The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Welcome back. We're now going to get into the demo portion of lecture 03. And so these demos are in the D4M API directory, in the examples. We've moved on from kind of the intro into the applications. And we're going to deal this one where we're dealing with entities extracted from this data set. So we go into the entity analysis directory, start my shell here. Yeah. Start our MATLAB session here. I always run MATLAB from the shell. If you prefer to run it from the IDE, that's fine. And again, our D4M code runs in a variety of environments, not just MATLAB. All right, so that's started up here. So let's before we do that, let's look at our data set here. So this is a nice little data set. It's about 2.4 megabytes of data. So, and this is the Reuters, some of the Reuters documents processed through our entity extractor here at Lincoln Laboratory. And so if I look at this, say, with Microsoft Excel, try that. All right, so you can see that pretty clearly, right? So we basically just have a row key here to read this in. We have a document column, which is the actual, widen that. That's the actual document that it appears in. We have the entity, just happen to be alphabetical here, the way that comes out. We have the word position in the document, so this tells you that this entity appeared in these positions in this document, and then various types, location, person, organization, those types of things. So that's what we extracted from these documents. There's no verbs here. It would just tell you, a person, a place, an organization appeared in this document and would say anything about what they're doing or anything like that. So, but this just shows examples of the kind of data that we have here. All right, so we'll close that. Save. Excel. All right. Let's go back to so the first thing we're going to do is the first script is entity analysis 1. We're going to read the data in. And actually, let's all right, there we go. So, and this is this first line, just reads this in. It's a fair amount of data. We're turning it all into an associative array. We have actually some faster parsers that will read it in, but just the read CSV is kind of the most general purpose one that's fairly nice. And so this is going to go, and we'll go back. It's running a whole bunch of stuff here, and then tries to pull together its graphics. All right. So there we go. So let's take a look at what we did here. So we read in the data into essentially an edge list associative array. Just displayed the first few rows here so you can see. So it's alphabetized or lexicographically sorted. The first column's always something to be aware of. That 1 and is then followed by 10 is then followed by 100, then by 1,000 in this sorting. Here's the documents. Here's the entity, there's the position. So it just looks like the normal table that we read in, but it is associative array. I'm now going to want to sort of pull this into our exploded schema, and this table didn't necessarily come to us in the easiest format to do that in, so there's a few tricks that we have to do. So we're going to go and get each document, basically. So we have a row, a column, and the doc, so that's the value. So this is whenever you do a query in an associative array, one of the powerful things about MATLAB is you can have variable numbers of output arguments, and you can change the behavior. So if I just wanted this to return, if I just set this to, A equals E this, I would have just gotten an associative array vector. But if I give it 3 output arguments, it'll say, oh, I'll give you the triples that went into constructing that. Because sometimes that's what you want to do. Also, it's faster. Because to do this, every time I do a sub-associative array, I effectively have to pull out the triples and then reconstitute the associative array, and that can take some time, and it just saves you a step. It goes directly to the triples, which is nice. So I basically say, give me the document column, give me the entity column, give me the position column, and now I have all of these, and since I know they're dense, I know that, these are all lined up. The first doc string and entity string and position string and type string are all. So that's me exploiting a little bit. I know that this is a dense table, and I'm not going to have any missing there. Now I'm going to interleave the type and entity strings. So I have this function called cat string. So basically, cat string takes one string list and another string list, and then it interleaves them with a separator, a single character separator. And now I can construct a new sparse matrix, which has docs for the row key, this new thing called type entity to be the columns, and then I'll just throw the position in as the value. And so that is our exploded schema that we just talked about, done for us in a couple lines. There's other functions that can do that for us as well. And since I don't want to repeat this, because it took a little while to read it in, I'm just going to save it as a MATLAB binary, which will then read in very quickly from now on, which is nice. So I can save it. There we go. Just to show you, if I show you the first entry here, so in the row, and then this just shows you, this is the different types of columns that were in that data set. So this is their row key here, and the various columns. These are the different columns, and then it shows you how many, the locations of the word in there. If I display it, I see that I ended up creating an associative array that consisted of almost 10,000 unique documents and 3,657 unique entities in that data set. And then we're going to take a look at that. We can do SPI and transpose. And if we look at here, zoom in on that, and you can see, zoom in, we can see different types of structures here. You can click on one of them. And that tells us that the location Singapore appeared in this document in these 2 word positions. So that's typically about how many lines it takes to take essentially a basic CSV file and cast it into the associative array to start doing real work. That's typically what we see. If you find it's getting a lot longer than that, then that probably means there's a trick that you're not quite getting, And again, we're always happy to help people do this. Very important step, this first taking your data and getting into this format so that you can do subsequent analysis on it. All right, let's close that. So let's go on to the next example here. So I'm going to do compute some basic statistics on this. Alrighty. That took a lot. See, that took a lot less time. Loading it in from a binary, much faster. Much faster. Very fast. I mean, Faster than if you had put it in a database and read it out of a database. Much faster to read it out of a file. So we always encourage people to do that. This just displays the size, so we have, that's what we had in the original data. NNZ shows the number of entries. So if we do NNZ, that's the number of entries. All right. I now want to undo what I did before. I want to convert it back into a dense table. I want to take all those values and convert, I want to take all those things that I appended to the column because I just want to count how many, I want to know how many locations, organizations, people I have. So we have this function here called call to type into another function that I forget the precise name that does the reverse, which basically give me an associative array, give me a delimiter for the columns, and I'm going to now rip that back apart, stick that back into the value position, and then you're going to now sort of essentially make it dense again. And so we do that. We then throw away the actual values, and so we do this double logi, which converts it all to ones, and then we can sum the rows. So we collapse along the rows. Now we have a count that tells me that in this data set I had 9,600 locations, organizations, people, time. Those are the distinct ones there. All right. Let's see here. We can count each entity. So we have our thing here. We just do the count. We can find the triples of so basically I've just done a sum. So this is the original exploded schema. I basically summed all the rows together, so I'm now getting a count for each unique entity. And I can find instead another way to get the triples is just to use the find command. It works the same way as it does in MATLAB. It will now give you a set of triples, a temp, which we don't really care about because we've collapsed that dimension. It'll be all ones, the actual entity and the count. And I'm going to create a new associative matrix out of that. So we now have the count and the entity, and I'm going to plot a histogram of that. So I'm going to go with my count things. I'm just going to get the locations out of that. So using the starts with command, I say get me all locations. I'm now going to just real math, and I say give me the adjacency matrix, which just returns a regular sparse matrix, and I can do sum, full, log, done. Now this is the classic degree distribution of all the locations in this data, and it shows us that certain locations are very common. A few of them are very common, and a few that is, they appear in most of the documents, and a lot of locations only appear in one document. So this is the classic, what we call power law degree distribution. Again, always a good thing to check. Sometimes you can't do this on the full data set, it's so large, but just even a sample, just to sort of, you kind of want to know this from the beginning. Am I dealing with something that looks like a power law, so like everything else, or, oh, what do you know? I see a big spike here. Well, what's that about? Or it looks like a bell curve or something like that. And so this is just really, computing means, good. Computing basic histograms, very good. Without this basic information, it's really hard to advance in detection theory. And this is probably where we take a slightly different philosophical approach than a lot of the data mining community, which tends to focus on just finding stuff that's interesting, where we tend to focus on understanding the data, modeling the data, coming up with models for what we're trying to find, and then doing that, rather than just sort of show me something interesting in the data. Show me a low probability covariance or something like that, which tends to be more the basis of sort of the data mining community. Although no doubt I probably offended them horribly by simplifying it that way, in which case I apologize to people in the data mining community. But here, more traditional detection theory, and the first thing you want to do is get the distribution, so you can typically one thing you'll do immediately is we put essentially what we call a low pass and a high pass filter on it. Things that only appear once are so unique that they give us no information, and things that appear everywhere, again, give us no information about the data. So you might just, have a low pass and a high pass filter here that just sort of eliminates these high end and low end types of things. A very standard signal processing technique that's just as relevant here as elsewhere. Alrighty. So statistics, histograms, all good things, easy to do in D4M on our data. Don't be afraid to take your data, bump it back into regular MATLAB arrays, and just do the regular things that you would do with MATLAB data, with MATLAB matrices. We highly encourage that. Now we're going to do the facet algorithm that I talked about in the lecture. So let's do that. All right, here. So once again, we've loaded our data in very quickly. We've decided to convert it directly to numeric, which is we're getting rid of all those word positions because we don't really care about them. I'm going to pick, so one thing I like about this data set, and for those of us who are a little older, you know, we remember the news of the 1990s. You know, this is all a trip to memory lane. For those of you a little younger who are in elementary school, this will not mean anything to you, but it's like, oh yes, a lot of stuff about the Clintons in this data set, so that's always fun. The first facet we're going to do is we want to look at the location New York and the person Michael Chang. Does anybody remember who Michael Chang was? Tennis player, yes. He was kind of like this hip tennis player. Used to battle Andre Agassi. So I don't know how long his career really lasted, but he was this is kind of right at his peak, I believe. So now there is, to show you that equation that I showed you in the slides wasn't a lie. So we take our edge or incidence matrix, we put in pick the column New York, then we pick the column Michael Chang. We need to do this no call thing because we now have a column vector with a column Michael Chang and a column New York. And if we added them together, well, they should have no intersection. So if we do the no call, it just sort of pops those two column names away. So now they're effectively both one, and we can add them together to find all the documents that contain both New York and Michael Chang. So we do that. So we've added them together. This is now a new column vector, okay? And we transpose it to make it a row vector. And then when we matrix multiply it back against the original data set, we've just computed the histogram of all the other entities that are in the documents that contain both Michael Chang and New York. And as we can see, Michael Chang appears 3 times, so that tells us there's 3 documents, and New York appears 3 times. But we also see Czech Republic and Austria and Spain and the United States. Anyone want to guess why Czech Republic? Was Ivan Lendl still playing then? I'm just wondering if he had a lot of matches against him then, or would he already kind of be into fade or something like that? I don't know. He's probably had some Czech arch rival or something like that. Or maybe there was just a tournament, and these are the type of thing. With the Reuters data sets, you do have the problem is that the person who types the article always puts the location of where they filed it. So New York could always be in these just because the person happens to be based in New York and they typed it from New York or something like that. So that's always fun. We can normalize this. So what I'm going to do is take the facets that we computed here and normalize it by their sums. Okay. So the facets is just showing how many times something showed up, but it doesn't tell me if it's like, well, is that something that is really common or really rare? So now we want to look at things that we want to see of the other entities that appeared in these documents, how many of them are really, really popular, and how many of them sort of really just only appear in these documents with Michael Chang in New York. So as you can see here, so we have Belarus, Czech Republic, Virginia for some reason, and this just shows you, look, these are in a lot of these have a very low, they're being divided by a fairly large number, which means that they appear in a lot of places. So they happen to appear in this same set of documents, but they happen to appear in a lot of documents, as opposed to Michael Joyce or Virginia Wade. That's a tennis tournament, right? The Virginia Wade tennis tournament or something like that. These appear more common and more likely to be something that is like, oh, that's a real sort of relation that exists between these entities. So it just shows you how you do that. Again, very powerful technique. Basic covariance type of math. So facet search, very powerful. All right, so I think that was 3, so we're moving on to 4. So now we're going to do some stuff with graphs. All kinds of graphs here, all kinds of graphs. All right. So once again, we loaded in our data very quickly. We're just going to make a copy of it. And then I'm going to basically now convert the original thing to numbers. So get rid of those positions. And now we're going to do, well, so before we did essentially the facets of the correlation between two things. But the real power of D4M is that for about the same amount of work, we can correlate everything simultaneously. So we're going to do square in, which basically is the same as E transpose times E. A little bit faster when we're doing self-correlations, but not too much. We could have typed E transpose times E. And then we're going to show the structure of that. So remember we had 3,657 unique entities. So now we've constructed a square matrix that's 3,600 by 3,600 unique entities, and we're going to plot that. So let's see here. Go to figure 1 here. So that is, hopefully this won't crash our computer. So this is the location by location. This is the full entity correlation matrix here. You can see all the structure. These are the location. So this block here is location by location correlation. This block here is person correlation. It obviously has a dense diagonal. It's symmetric. And then down here are the time correlations. And so these, in fact, the first thing you'll probably notice is these dense blocks of time have to deal with the fact that this is a finite set of Reuters documents. There's only 35 unique days or times associated with the documents themselves. So those are showing you the times that are associated with the document reference. So that would be this type of structure shows, oh, well, if I want to just get the times that were, associated with reporting, I can get that. Or if I want to do, they're referring to some date. And you can see there's times that are in the past and in the future and various types of things like that. And that shows you the structure. So this is a very nice structure. We can zoom in here. And then you see, and more substructures emerge here. Oh, what's that one? What's that one? Let me take a look here. What's this? United States, very popular, dense. You see that very dense thing like the United States here. Who's this? This is probably America or something like that. United Nations Security Council, very popular. Oh, we're in the organizations here. Yeah, we don't have so many of them, but it's the most popular. So you can just get this feel of the data. Very powerful, because often, for the most part, when you work with your customer and you do this, you can be just about 100% sure you're the first person to actually get a high-level view of the overall structure of the data. Again, a very powerful perspective, because they simply just don't have a way to do this. And using the sparse matrix as a way to sort of view the data is very, very powerful. All right, so let's get rid of that. So we did the entity graph. Again, what we do is just whenever we take an incidence matrix and we sort of square it or correlate it, then the result is an adjacency matrix or a graph between those two things. So again, adjacency matrices are a projection from the incidence matrix. We've lost some information. We've always thrown away some information in doing that. But often that's exactly what we want to do. We want to project it down into a subspace that we find more interesting. Something else that we can do is let's just look at the people beginning with J. All right. So I'm going to just create a little starts with entity range here with our starts with command. I can pass that into here to grid just the records that have the entity P, and I'm going to do the correlation of them using this pedigree preserving matrix multiply that we have, this very special one. So we'll go take a look at that, and that will explain what I mean by pedigree preserving. So we go here. So again, this shows you the all the people that appear together beginning with the name J, and it's of course again a symmetric matrix, this dense diagonal. You click on it, it tells you. So Jennifer Hurley and James Harvey appeared in this document together. So when we do that special matrix multiply, it doesn't preserve the values in the normal matrix multiply sense. Instead, it preserves the label of the common dimension that's eliminated. So when you do matrix multiply, you're eliminating a dimension. Well, we now take that common intersection and throw that in the value. So you can now say, Jennifer Hurley, James Harvey were connected by this document. And so a very powerful tool for doing that. You notice I restricted it to J. Why didn't I just do the whole thing? Well, you see this dense diagonal here. Let's click here. If you had a very popular person, look at all the hits we're going to get when we correlate it with itself. Okay? This becomes a performance bottleneck when we start creating enormously long values. And so we always have to be careful when we do these pedigree preserving correlations. If it's correlating one set with another, we're not going to have a dense diagonal. It's going to be fine. But if we're correlating something with itself, we always have to be on the lookout that we might be creating these dense diagonals, in which case we could have an issue that we might create a very, very large value. And the fact of the matter is the way we sort the strings is we convert the list to a dense car matrix and then call the MATLAB sort routine. It's the only way we can sort it. And so the width of that matrix is the length of the longest string in the list. So they're all about the same length, it's fine, but if you have mostly things that are 20 characters and then you have something that's 2,000 characters long and you create a 100,000 by 2,000 matrix, you have just consumed an awful lot of memory, and sorting that and all that just sort of. So whenever people say it's slow or they run out of memory, it's almost always because they're creating, they have a string list, and we're trying to manipulate by sorting, and one of the values in that string list is just extremely long. So that's just a little caveat there. Very powerful technique. You have to watch out for this diagonal. And there's ways to work around it that usually are data specific. But again, a very powerful, this pedigree preserving correlation, something that usually people want. And especially since we almost usually store just like a 1 in the value, we're not really throwing away any information. Sometimes we want it because we want to count how many times that those happen. If we didn't do the pedigree preserving, the cat key mul, then we would have gotten a value of 3 here, and so we could have counted. That would have told us. Sometimes we do them both. One that gives us the count, one that gives us the pedigree, and just store them both. And there's different things that we do with one versus the other. So again, having fun with the different types of matrix multiplies that we can do in this in the space of associative arrays. All right, we're running out of time here, but I think we're almost done. Oh, so let me just see here. And then we did the document-document correlation. So this is the square out, which is E times E transpose. And we'll just take a quick look at that. So again, here we are, figure 4. This just shows us which documents are closely related to each other, which documents have a lot of common entities. So this just says here that these two documents share, had one common entity with them. Other ones, I'm just clicking around here, not having a lot of luck finding one that's got a lot in it. So maybe around here. No. Right. Well, certainly if I click on the diagonal. Oh, wow. So these are basically pretty sparse correlations between these documents. So, all right, and I think we'll go now to the last example. Is there a last example? Yes, one last one. So we'll do EA 5. Alrighty. So now we'll do the stuff I showed you so far is pretty easy stuff. Pretty sophisticated by a lot of the standards that are out there in terms of just being able to do sums and histograms and basic correlations. That's often significantly beyond what is just sort of the run-of-the-mill, which you'll just run into if you just go into a place that does doing basic analysis. So again, we load it, we convert everything to numeric. We've now squared it, so we created the graph. I wanted to get rid of that annoying diagonal, so I got the diagonal out. So just so you know, so all I did is I know it's a square, so I can do certain things without worrying. So I can basically take the adjacency matrix, that just gives me a regular MATLAB sparse matrix. I can now take the diag of that, and since it's a square, I can just take those two, subtract them from each other, and just insert it back in without any harm done, knowing it's like, look, I took a square adjacency matrix out, did some manipulation, stuff it back in. The dimensions are the same. It should be okay. I might have an issue that I may have introduced an empty row or an empty column, which could cause me a little problems. I'm not going to get the triples of that because I want to normalize the values here. So I'm going to get the diagonals showed me how many counts were in each document. So I want to normalize any entities in that document because sometimes you'll get a document, it's like, and here's the list of every single country that have participated in this UN meeting. And it'll have, 100 and some countries. So a country appearing in that document is not such a big deal because all the countries appear in that document. So this allows us to do that. We can, if we want to do a correlation, we take the actual value and then divide it by the minimum, the least document. That'd be the maximum number of hits you could get in a correlation. We can now do multifaceted queries. So we want to do location against all people. And so here's a more complicated query which says, find me all people that appeared more than 4 times and with a probability greater than 0.3 and with respect to New York. So here's New York and all these different people who are basically, these are people that appeared with New York and almost exclusively appeared with New York. So John Kennedy, so this is his son that was still alive at that time. Was sort of very popular in the news, so let's focus on him. So let's get John Kennedy. Let's get his neighborhood. So we can go into his get all the other people who appeared in documents with John Kennedy, and we can plot that neighborhood. And if we go here, this is his neighborhood. So there's John Kennedy, his rows and columns, and then these are all the other people that appeared with him. You see this dense row and column. And then these are what are called the triangles. So these are other people who appeared in documents together. So George Bush and Jim Wright appeared in a document together, but not necessarily with John Kennedy. And we can actually find those people by just doing this basic arithmetic here. And this shows us all the triangles, all the other people who also appeared in documents together who appeared with John Kennedy. And so that's what you have. So with that, we're running a little bit late here, so we will wrap it up. And, again, encourage you to go into your code and run these examples and try them out. And this should give you the first sense of really kind of working with some real data and playing with stuff. So thank you very much.